Oh.
Back at 12 o'clock.
Yeah. Okay, where was I? Oh yeah, I was going to do multi-dose PK was 2 NCP, right? Okay, let's look at the stuff that's different. Okay, well, under data, the thing that's different is now I've got a situation where I have NOBs and IOBs here are indicating where the observed, the non-censored, the observed non-censored data is located, which records correspond to those, and NBQL and IBQL are now telling me where the BQL data is in my set of records. So that's taken care of. I specify the yellow Q here. This one's simple because I'm just saying it's the same for all of the samples. We could do a little additional bookkeeping if they were different for different samples. Okay, so we got that in there. Let's see, I don't think I do anything in transform data related to that. Yeah. Parameters, I don't think I do anything in there related to that. Where it comes down is when we get to the model section. Come on. Too much stuff going on, too many comments. Actually, let's move this thing over so much wrapping. Okay, here's where stuff happens. Basically one line at this point. So in addition to having my log C obs here being related to the normal distribution for all of the ones where I have observed data, I have my subset where I've got BQL cases. I guess there must have been another step up there I didn't show where I pulled out the C hats that correspond to the BQL data, which is pretty straight ahead. So I'm saying target plus equals normal LCDF. I take since I'm again working on our log normal, it's the log of the LOQ in here, and then the log of my predicted value and my sigma. And that takes care of, I don't know, I always forget is that M3? Okay, so for those that are, into non-memish things, I think they call that method the equivalent of M3.
So what would happen if you switched those two lines, 148 and 149?
Oh, wouldn't care less.
So
because one doesn't depend on the other in any way.
Okay, so it doesn't?
No, because these two are working with disjoint. What's inside here and what's inside here are two disjoint collections.
But eventually they're going to be added to give one.
Yeah, but it's just an addition, and addition is commutative.
Same as in dynamics, it's also independent there. Just if statements.
Yeah, I think I didn't consider that the tilde notation is somehow possible.
Yeah, it's all addition. Okay, so that's pretty much the story for dealing with BQL data, in particular one type of sensor in here. So that's as far as I was going to actually take that. And I guess that may also reflect a bias I have. I'm one of those that I get a little anal about a couple of things. One of them is I almost never throw out BQL data. So I know a lot of people there. I go, okay, do you keep them? Do you throw it out? You keep them because it's so easy to deal with.
Is it also true for the model, how STEM behaves as a model in computation?
Where you can run into problems sometime is if it hits a sampling region where that basically says a BLQ is impossible. So that can sometimes happen, and occasionally you'll have to try and bulletproof things so that you don't end up with it basically throwing an infinity at you.
Okay. And if you have non-mem, you really need to, if you have a couple of samples, consecutive samples, with BQL data in it, you certainly need to throw out the last samples, or you keep the first one as BQL. Because otherwise it gets biased. That you get, you basically say that it is the same probability for all those samples.
It shouldn't be the same probability for all those samples because the predicted concentration changes.
the concentration changes, but the region where the probability is stays the same level. So the
Yeah, but the probabilities all change, and as you go, and normally for something where it's going to be a decreasing profile, the probability gets higher and higher that it's BQL.
that's just a way for me, for myself to.
Yeah, I suspect that's more of a quirk of using an optimization method with some of these things sometimes. But in principle, it's information. The fact that you happen to hit a BQL once could actually be a fairly improbable event, and because we've all seen data where you have one dip below and then the next one is above. So I guess my bias is there's no theoretical reason for why you should throw them out. Now, on the other hand, if you have a whole big string of them, they become decreasingly less informative regarding your parameter estimates. So it also falls into the heading of it probably doesn't hurt. Okay, so the next thing I wanted to move to, which what we just talked about also helps us when we think about this target plus equals kind of thing, is the idea of defining your own probability functions and likelihoods. So say your user-defined functions are not limited just to the deterministic calculations. We can use it to help us specify both likelihoods and sampling things. So you can write those. And as I mentioned before, you can write pretty much any likelihood using the target plus equals statement. And we'll see that in our hands-on session 4, because it's kind of what we're building towards on this. For user-defined log probability density function, so again, it's remembering that what's going on with Stan is underlying there is it's calculating this log probability and using that to increment the overall log probability. So a user-defined probability function must also calculate log probability. So the function has to end in underscore LPDF, if it's, well, assuming it's a density. So if it's a probability density function or the log of the probability, you would end it with underscore LPDF. You can use that in both sampling and target plus equal statements. So, for example, let's say I wrote a function that I called myfun underscore LPDF with the arguments, y, what have I got, y, theta 1, theta 2. I can write that either in terms of a sampling statement using a tilde, in which case I would write it in terms of y tilde myfun and only the last two arguments, the theta 1 and theta 2 that I'd be trading as parameters of the distribution, versus the target plus equals version where I also include the data. Basically what happens is this gets translated in effect to this anyway, where the y is really treated as a function argument. But I can write it either way in here. And as an illustration, I do a function which is kind of silly because you can actually do truncated distributions in Stan easier than this, but it just illustrates how you can do it. To write your own. So here I'm going to call it real normal trunc underscore LPDF. The first argument is going to be my data type item here. And then I've got a mean, a sigma, and then a lower and upper bound. And here's my arguments. And the core in here, so if y is between the bounds, then the result is going to be equal to, normal underscore LPDF in here, where I basically do that. And all of it, well, this actually would probably read much more easily if I wrote it without the logs, because underneath basically what you're doing is taking the normal density and then dividing it by the probability of the normal thing from the lower to the upper bound, and that gives you your truncated density in there. Basically, it's just renormalizing the density, so it appropriately integrates to 1 when you go between the lower and upper bound. And then if it gets outside there, then it's negative infinity, which if you actually go there is probably a bad thing, and it'll kill the sampling anyway, because if it's really a truncated normal, you better have bounded your random variable by that anyway. Okay, but that would be an example of writing such a function. And do I even, I'm actually not, this is one place where I think I'll do a little triage and cut short so we can move to some other stuff. If you want to see that sort of in action, there's an example in here that I basically took that first thing, that FXA inhibit average, that very first one we looked at, and stuck a truncated normal in there just to illustrate using a user-defined probability density function. So that takes us to hands-on 4 in here, which is going to be a parametric time-to-event model. So as one might expect with a time-to-event model, we're going to have some right censoring as part of this. And this one sort of tries to toss a bunch of stuff into the hopper to sort of see them all going in at once here. So it's some of the last stuff I talked about, but we also bring in our ODE solvers and stuff like that as part of the picture. So what I'm going to do is we're going to analyze the time to a peripheral neuropathy event. In particular, we're talking about a case where they've, where the peripheral neuropathy have been reported as adverse events and graded from 0 to 4 or whatever. And we're in particular going to look at the time to the first grade event of 2 or greater in here. So that's why I call it grade 2 plus peripheral neuropathy event in patients treated with this antibody drug conjugate delivering this monomethyl RStan E, MMAE. We're going to simulate and analyze data using a simplified version of the real case. So the case I'm doing here is actually a concocted case that oversimplifies it just to illustrate the key points I want without keeping all the complications. But it's based on a model that I had done in conjunction with a client project here. Okay, so we're going to have, instead of, what was it here? It was, polatuzumab vedotin. This is going to be folatuzumab vedotin, okay? And so we're going to look at time to grade 2 plus. We've got 3 treatment arms that correspond to different dose levels, 1.2, 1.8, and 2.4 milligrams per kilogram given every 3 weeks for 6 doses. We've got 20 patients per treatment arm, and these are looking at some Kaplan-Meier curves for that particular case. Now, for a time to event, that's actually not a very large number to work with, but fortunately we had a fair number of events in this. So you can see, it's kind of probably hard to see the colors there, but you've got the 1.2 milligram, you're coming up here, but in the end it ends up sort of the lowest one. There's a lot of noise in here because, again, the sample size isn't very big. The 1.8 actually starts out higher, but ends up more or less following along with the 2.4, and the 2.4 finally is the green one here. So, yeah, there's something going on there, but by the way, if you give no drug, you don't see it at all. So it's clear the drug's doing something. Excuse me. But the dose response is a little hazy. By the way, this is simulated data where there is an underlying model that has a clear dose response, so this is just noise. Some of that's just pure noise, which is just a reminder that be careful how much you interpret data. You might be over-interpreting things. Okay, so the model here, I'm going to do this. We've got a PK model, and this was a simplification, a major simplification of the PK model here. Just to keep it simple, I just made it a 1-compartment model. In addition, normally when I would do this kind of model, I would simultaneously deal with both the PK and the PD. But just to keep it tighter and shorter on the explanation, I'm going to cheat and just take some fixed values for clearance and p-values for all the patients, pass them in, and only work on estimating the PD. So keep it tighter. In fact, I'll quickly mention, do I have it? Yeah, you'll see that in a model that's called TTPN2. There actually is a TTPN1 in your stuff too, which is actually a more complete set that does do the simultaneous fit, in case you want to explore that too. So in here, so for the PD, I'm going to have, well, what we found in this is the hazards seem to be significantly delayed relative to the drug exposure. Roughly speaking, it almost looked like it had more to do with cumulative drug exposure than it did to an instantaneous drug exposure. And in fact, if you did something kind of silly like use a cumulative AUC for the drug concentrations, that actually correlated much more strongly with the events and with the apparent hazard than did the sorry, not with the event, but sort of with the apparent hazard than the concentrations themselves. Now we know that it's possible to recover from this, so truly doing it as a cumulative AUC didn't make sense, since that would imply no recovery at all. So we did. So instead, what we've incorporated is an indirect action model where the delay is relatively large that's introduced by that. In addition, there seemed to be some increase in the hazard that wasn't completely explained by the indirect action model, and that was captured in a in sort of a Weibull sort of model as part of this that seemed to capture that. So our likelihood for this then, again, we've got both observed and censored data, because we have, while we have events in a lot of the patients here, there are a few patients where there were no events, so we do have some right censoring in this, so we have to deal with that. Okay, so we got, oh, where was it going? I was over here. So we have to specify likelihoods both for the first case is where there's no censoring, the second is where there's censoring. So in the case where there's no censoring, the probability density function is we've written here in terms of the hazard. So the way this is being written is the hazard is a function of drug exposure and time, and so the likelihood then becomes a function of that hazard in this form, where you take the hazard at a given at the time at which the event occurs times e to the minus this integral, the integrated hazard, where you integrate from 0 up to the event time, and you integrate the hazard there. By the way, if you ignore that part is what's often termed survival of function, because it's equivalent to the probability that event occurred after that time. And then, whereas for the censored case, you actually do use the survival function directly, which is basically this right-hand component here, where it's e up to, in this case, the TPN represents not the time at which an event occurred, but the last time at which you have an observation for that individual, and therefore it's a right censoring time in there. So I have to have separate likelihoods for those two cases. Let's see, is there anything I missed over here? I think not. You know, they're pointing out I'm using 1 to indicate censored and 0 to indicate not censored. And my hazard of peripheral neuropathy grade 2+, I'm using a hazard based on the Weibull distribution that I've written out like this. So you can see it's the hazard equals some parameter beta times a drug effect component raised to the beta, all times t raised to the beta minus 1. E drug here, I'm just going to use a simple linear one in this case. And the whatever, I guess I use an E is implying an effect compartment. Or actually, well, maybe I did use an effect compartment. I kept on using, oh, I did use an effect, sorry. I know one of the we tried other models too, which included the indirect action. Okay, so I've got an effect compartment model here that's incorporated into that. The overall ODE system that I'm going to specify in this is basically going to be our model for our one compartment model. It's an IV dose, so no problem there. That's easy to deal with. And I've got my my effect compartment. And then I'm doing this, well, I'm including the hazard as part of this because I want to calculate that survival function, which involves calculating the integral of the hazard going from 0 to some particular time. So my x3 then is going to be equivalent to that cumulative hazard, which I will want for my likelihood calculations. Okay, so let's do a quick illustration on that. And okay, move this over so I can see it. Let's go to this, we're in stan, yep. So we're gonna look at ttpm2.stan. Okay, so first thing I do is specify, or first thing in the list here is my functions block with my ODE functions in here. So this is pretty straight ahead representation of that set of 3 ODEs we already saw. So we can see here my dxdt1 and 2 is just my PK, my effect compartment, and then finally my hazard. This thing again is a little bulletproofing to make sure that it's not returning I'm not trying to shove in here a hazard that's less, no, what is it? Oh no, it's just simplifying it because I know at time 0, the hazard is 0 in here, which is actually appropriate, and that's to avoid doing 0 to something which the stan doesn't like a whole lot. Depending upon what the value of beta. It's fine unless beta is less than 1, in which case it doesn't behave well. 0 to a minus thing it barfs on. Okay, so that's all there is to that part. We play a few games here. Instead of N subjects, I called it NID. NT, that's all the same. Okay, so I've got sort of the same games as before. I have a number of observations and the indexes of the observations, and I do the same thing for the censored case, censored events, and a corresponding I for the censored events. The rest of it is same old, same old. Okay, what we got in here? That's all stuff in here. I'm just filling in the SS value because we're not actually using it here. Ditto for F and T lag, nothing new there. Oh yeah, I'm sitting here forgetting my observations are actually in terms of time. So some of these are being set up. I know where I'm at. Okay. Actually trying to remind myself what the heck T-pred was about. Oh, that's right. I was setting up things to do some things to do some posterior predictive checks. I'm not going to dig into that in great detail here, but what I was actually going to do is rather than try to simulate the predicted times to event, I'm instead going to simulate the hazard. Actually, what did I end up simulating? I think I actually simulated the cumulative density function for the time to event, which I returned to R, and in R I dealt with the simulated times given that CDF. And okay, transform parameters should be where the major stuff hits. So we're sampling over the individuals again. I package up the parameters that I pass to my differential equation solver, which here I'm passing the function we defined up in the functions block, and everything else is just the usual thing we've done before for passing the various arguments. Okay, and here the first steps I'm going on is kind of setting up to calculate my my likelihoods in here. So in here I'm calculating the survival function for the observed values in here, and so you can see things where I'll ignore the machine precision thing for a moment. I'm taking e to the minus this whole mess here. Well, this x IP and ob. So this is just pulling out the predicted x's, or the predicted cumulative hazards for, since it's the third item here, so it's pulling out the predicted cumulative hazards for the cases where we have observed events in here. Let's see, I think the e-drug obs was only there to be able to pass those values on. I actually do use them. Okay, so I can do the E-drug corresponding to those. In here I calculate the corresponding hazard. I could have, it might have been nicer to do that as a separate function and call that from both the function up top and this now that I think of it, but I didn't, so I did it here again. So I'm calculating the hazard because in the end to calculate my, okay, oh, that's going to be down in the model. I need both the hazard and the cumulative hazard to calculate the likelihood for the observed events. And then for the censored events, I just need to calculate the cumulative likelihood, so I do that here. By the way, another alternative I could have done is I could have calculated the survival function for both and then extracted the subset of them that corresponded. In fact, in hindsight, it probably would have been more readable if I did that. And then finally, down in the model section is where I do, again, that's the stochastic part of it, so this is where I'm actually calculating the corresponding likelihoods. So here I take my, recall again that the appropriate likelihood for the observed events is going to be the hazard times the survival function. And that's what I'm doing here. And then I take the log to get it as log probability. And then for the censored events, it's just the log of the survival function. So again, this is a case where you've got user-specified likelihoods entirely. And yeah, there's nothing more. In fact, generated quantities I think is a, yeah, generated quantities does have more going with it. I think because of time, I'm not going to go through it in detail, but just so you get a clue as to what I'm trying to do, I'm calculating the cumulative density function for the events, for these events, and I'm going to pass that back to R. Now, once I have the cumulative density function, I can use sort of the classic inverse strategy for generating random samples, because if you've got a CDF, you can take the inverse of that CDF, and when you take the inverse, and then if you take that inverse CDF function and calculate it at a value corresponding to a uniform 0-1 random variable, the result of that will be a sample, a random sample from that distribution. So that was, to me, the easiest way to deal with it here was to basically do that. And it's fairly, if you want to take a look at the R script in here, you'll see it basically does use to do the inverse. When you know you've got something which is monotonic like that, you can easily do the inverse in R just using the approx function, which does a piecewise linear interpolation, and you just flip the arguments. So what would normally be x and y, you flip them. And if you pass then the uniform 0-1s to that, you get back your samples. So that's a fairly simplistic strategy for doing the random sampling for this. And the very nature of these calculations would enforce that monotonicity here. And if we'll see, we're kind of coming shorter and shorter on time. So if for some strange reason we have more time, we'll come back to the details of that. But I wanted to get basically the framework again, that we put together these elements that use the whole target plus equals thing in here to specify any user-specified likelihood you want in here. And we also tied that into pulling in our ODE solver and the whole mess in here to do that for what is actually a very complicated looking likelihood. Okay, oh, wrong one, there we go. This you can take a look at later, I guess. This is just mentioning some other pharmacometrics related resources that are out there. I haven't actually looked at, oh no, the first one is something actually Charles Margosian put most of the first one together. Nice, he did a little wiki page out there on the Stan Dev site. A while back, Wang Zhang and when Ping Wang put together a a package called RStan that has some similar flavors to Torsten in there, although it was much more R-bound than what we've done so far. But it was a nice little bit of work that was done there. I believe that's still there. Actually didn't double check these links to make sure they're still there, but I believe so. And Sebastian Weber at one time did some examples of models written directly in the Stan language. Okay, the next thing is probably more philosophical on kind of where I think things fit and where I think they're going with Stan and Torsten. So Stan's big thing really is it's very flexible. Okay, it's a very flexible platform for fully Bayesian analysis, particularly in cases where they can't be implemented in more standard PMX packages, like non-mem or monoliths, or at least not without making significant compromises. So that's its main claim to fame, if you like. You can do more routine POP-PK and POP-PK-PD analysis with Stan, particularly using the Torsten extensions, but as you've seen in here, it puts a fair amount of onus on individuals to do programming. Okay, non-mem and monoliths assume make pretty strong assumptions regarding the basic stochastic structure of the model. So a lot of that stuff is all under the hood, and you don't have to monkey with it. You're mainly focusing on writing the conditional, either the conditional predictions or conditional likelihood for one observation for one individual when you're working in a non-mem context. Whereas here you've got to think about the entire stochastic structure and deal with all of the individuals and all of the observations in the programming process. So that means there's, it takes longer to implement a model, until you kind of have a bunch of templates sort of built up for doing them. Also, computation time makes it non-optimal for a lot of those applications. MCMC, particularly if you have large large data sets and that, even if they're use analytical solutions, can take much longer than using optimization methods, particularly things like FOCE. So when you're trying to crank through things, particularly when you've got to discriminate between multiple models, it may just not be feasible to use Stan in that kind of a context at the moment. And so my current bottom line on here, at least my bottom line for current use of Stan, is I'd save it mainly for problems where, one, fully Bayesian methods are particularly useful, where you're incorporating informative priors, and the more flexible model specification language is needed, or at least strongly desired, for the problem you're working with. Because that's when it's going to pay off strongly in terms of helping you with a given problem. And the barriers that I see, the main barriers I see for the more routine use of Stan for those kinds of applications is, one, the computation required for adequate MCMC sampling, and the programming time required to implement typical POP-PK-PD models, which takes us to the shape of Stan to come. Again, I'm a jazz fan, so you get a jazz album. And we're in Montreux anyway, so let's take a look at the Stan. I'll say the Stan and Torsten development plans that I'm most familiar with and to some degree involved with. There's actually the overall Stan development plans go much broader than the ones I'm focusing on, but these are the ones that I have some tie to, particularly because we're actually doing a thing that's actually funded, of all things, by the Office of Naval Research to help do some of these things. It's actually a collaborative grant to both us and Columbia. Okay, one is to get some better, fast, approximate Bayesian methods. The first of those is likely to be something like gradient-based marginal optimization for marginal maximum generalized likelihood estimation. So basically, you're trying to go for good estimates of posterior modes in this, and also come up with some complementary elements for characterizing the uncertainty as part of that. And the others are a couple things that are directed more at big data sets, this sort of data streaming variational Bayes and this data parallel variational Bayes are both strategies that are trying to make it possible to, again, deal with much larger scale data than is currently feasible. The first one, though, the GMO or something like it, is probably the most relevant to our cases. The other is one of the things that that non-mem can definitely hang over Stan's head on this one is the lack of within-chain parallel computation. Okay, fortunately, see, non-mem again is working with a particular stochastic structure, so it knows it's almost always dealing with a situation where it can break the data up into pieces that relate to like individuals, and do the sort of, well, you know, what you can think of as either post hoc Bayes or actually even formal Bayes estimates for those individuals condition on the population estimates, and that's what it takes advantage of in order for its parallel processing, and it's taken advantage of that with its Bayesian methods, both the Gibbs Metropolis methods as well as the HMC method that they've implemented in non-mem. So for larger scale models, that is particularly advantageous. And you can't really currently do that in Stan, but there is now prototype code that is capable of doing that, and it's matured to the point that it will probably either be in either the next version or the one immediately following that. So look out in version 2.18 or 2.19, it will probably appear there, and that will definitely be a major improvement when you're dealing with models where each iteration is an expensive thing, like many ODE models, particularly if they're large-scale ODE models. The other things we're looking at is other flavors of differential equations. Differential algebraic equations, where there's a component in there where you have to deal with some solution of a nonlinear algebraic problem along with your ODE solution. Partial differential equations. So, for example, if you're dealing with, some of the models I've seen are things like solid tumor models, where you have to deal with spatial variations in various ways. There's the tumor growth and contraction, which is dealing with the other two dimensions here, or other three if you like, in here, as well as drug penetration, which makes it difficult to approximate those things as just simple discrete compartments. So anyway, there are reasons, particularly when we get into the QSP realm, where partial differential equations make sense, and finally stochastic differential equations, particularly when we start getting down into more fundamental systems biology kind of things and that. So those we're looking at. DAEs are almost there. We haven't made the final connection to the Stan language, but that's close. The other two were only at the early stages. PDEs are going to take a while. Fortunately, too bad Yi's not here. Yi Zhang recently joined us. He actually was working in a commercial framework where they were doing PDE work all the time, and is quite familiar with the methodologies there, and will be heavily responsible for implementing those. And he's already done a number of contributions. For instance, the DAE work he's already pulled in. And then I've alluded a few times to a couple R packages, both to doing pre-processing and post-processing, to try and take some of the programming burden off, because again, that's also a barrier to using these for production purposes. So I'm going to be at least modest, a little bold here, and argue that the addition of those features should make Stan and Torsten a superior open source alternative to, and then put your favorite PMX platform here. That's at least our ambition. And the other ambition here is to try and make this platform and Bayesian approaches plausible options for dealing with more complex, things like physiologic PK/PD and QSP modeling applications that are dealing with larger scale systems of ODEs and such as part of the problem, and bringing those into a realm where we can actually use a tool like this for I guess what in those realms they often like to talk about model calibration, and to have more formal model calibration methods available to them using Bayesian strategies. Okay, so that's that's where we're going. This is probably at least a couple of these. I think some of the critical ones are probably a 1 to 2 year time range. Really having PDEs flying, I think, might be pushing a bit longer than that. But that's where we're trying to go. I guess I promised to do them before I retire, so getting there though. I already promised Mark I'd stick around till I was 70, so anyway, hate to tell you that's not far off. Okay, what didn't we cover? We didn't really talk about categorical and count kinds of data. What I guess Stuart Beale used to like to call odd type data. The closest we got, we did at least one time to event thing here. Doing population and trial simulations based on the MCMC samples you got here. We didn't really go there. Mixture models and some of the hurdles you have to do here where you can't deal with discrete parameters. I didn't work with any of the other STAN interfaces. We only looked at RStan. I actually used command stan, not for everything, but during development processes. It's often quicker to sort of pull together the stuff I can do with command stan for doing early prototyping, so I often work in that environment. Sometimes it's also easy to pull out some diagnostics. Interfacing with external C++ code can be done, and that gives you a reference to a place to look at that. Fancier change of variable. There are situations where you have to formally deal with a change of variable in a way where you actually have to alter the distribution to account for that. We haven't gone there. There is an approximate Bayesian method built into STAN already called ADVI, and we didn't look at that. But occasionally that actually works pretty well, but it's difficult to be sure when it works well and isn't, so it hasn't been pushed too hard. We haven't used STAN for point estimation, which is possible. There is something in there called there's an optimization method in there, so you can do what could be called penalized maximum likelihood in here in calculating posterior modes. That's already possible. I haven't had a lot of experience with that, and it can be quite challenging depending upon the model, but it is possible. And ... There's, of course, plenty that I haven't done in here. And I should close with some credit where it's due in all of this. Most of the serious programming that's gone on in Torsten has been done originally by Charles Margosian, who's now actually at Columbia. He's a graduate student now in their statistics department. So he's hanging out with the same folks he worked with for some of this that were at Columbia. Yi Zhang, I talked about, has joined us and has been contributing quite a bit already. Of course, Mark Gassingay, our fearless leader, has made it possible and has encouraged these kinds of efforts. You may have seen that Metrum does generate a fair amount of open source tools available, and we've got a working philosophy there that really makes that desirable, feasible, and so on in here. And these things that we're generating now, for example, the stuff we do for STAN, I can't imagine a situation where that will become purely commercial. We may incorporate it into a commercial framework like MetWorks, but the components themselves would remain open source and free. There's the core STAN development team, particularly the group out of Columbia that I list here. Andrew Gelman, Bob Carpenter, Mike Betancourt, Daniel Lee, been involved in a lot of the stuff we did. Now, the STAN overall has a lot of other contributors. Major ones would be like Aki Bakari, for example, out there. Sebastian Weber, I mentioned before, was largely responsible for the current set of ODE solvers that are in STAN. We've had funding, external funding from both Bill and Melinda Gates and the Office of Naval Research through their through an STTR program, which is like an SBIR, but where it's an SBIR where you also have to collaborate with a nonprofit research institution, which in this case is Columbia. And after that, I give you a bunch of references. Any place where I had references are actually included at the end there. And scene. So anybody got anything left? I'm not sure I do.
I just want to say that I found it extremely impressive what you can do. I also will acknowledge that my mind towards the end went in the opposite direction of the complexity of the models that you presented.
Okay.
So I'll have to do a little bit of homework. But I'll do
Yeah, well, it's too much stuff in too short a time, so
Yeah.
unfortunately, these workshops tend to be more about letting you know what's there
Yeah.
than actually teaching you what's there.
Now, what is great is that the templates are there, so we can play with that. I also think that I speak for myself, but I work with sometimes larger problems. I do believe that this is the future, Bayesian stuff, and I think that the boundaries that you guys are working on, such as computation problems and inefficiencies to deal with that, that's going to make a huge difference. And will make me use that as well.
Good, thank you.
And I think everybody agrees, right?
Yeah, we're not in England where everybody should go, here, here!
Yeah. There you go.
Or for he's a jolly good fellow or whatever. I don't know.
There you go.
I started to run this last example, but it takes quite a while.
It takes a while, yeah. And if you do the TTPN one, it takes even longer, so yeah.
And that's because of the ODEs?
Because the ODEs are the same, but I'm also estimating the PK parameters as part of that. So it goes from in one case there's actually no hierarchy in the model because I'm not estimating the PK parameters because those are the only things that have I don't think I had any inter-individual variability in this in there, but the TTPN one does. So the dimensionality grows. So that's the main issue, is the dimensionality. I mean, keep in mind on these things, you're always, the overall dimensionality of the likelihoods we're working with are not just the population parameters. It also includes all the random effects in there. And that's the space you're searching around. Okay, well, thank you very much.
Well, thank you.
Glad you.
Great.